In this module, we're going to talk about molecular polarity. That is, whether or not a molecule overall is polar or not. Now, what we've seen before is how to tell whether or not a bond is polar. All we do is look at the difference in electronegativities of the two atoms involved in the bond. And if it was bigger than 0.4, it's a polar bond. Now, polar covalent. Now, for a molecule to be polar, overall, there has to be at least one polar bond in it. There can be more than one. But if there are no polar bonds in a molecule, then no matter what, that's just a non-polar molecule, period. There is no dipole moment, we say. So for example, a hydrocarbon, all carbons and hydrogens, no matter what, that's always going to be non-polar. Now remember, when you have a polar bond, the more electronegative atom, we can think about it as pulling the electrons away from the electronegative atom, creating a dipole, a positive end and a negative end. Now what happens in a molecule is that all the bonds are pulling against each other. They're pulling on each other. They're all shifting those electrons around. And if the net result of that is that the electrons are shifted one way or the other, then there's a positive part and a negative part, and it's a polar molecule. There's a net dipole moment. Although if the poles all cancel each other out, that happens too. You can have polar bonds in a molecule, yet have that molecule be nonpolar. So we're going to look at that right now. So we're going to look at how many bonds there are to a central atom and look at the possibilities. Now remember, I'm assuming in all of these that the bonds, there's at least one polar bond. Because if there wasn't, it would just be nonpolar no matter what. Now if there's two bonds to a central atom, then we could have a linear molecule. And if that molecule is linear, then if the two atoms that are attached to the central atom are the same element, they have the same electronegativities, then this molecule will be nonpolar. Because even though this bond right here would be polar, and so would this, the net result is that the electrons don't shift one way or the other because the poles cancel out. So this would be nonpolar. On the other hand, if we have different elements attached to the central atom, they're probably going to have different electronegativities. And if they do, then one element's going to be more of the outside atoms is going to be more electronegative than the other, and the electrons overall will be shifted one way or the other. The poles won't cancel out. And so now in this case, we would have a linear molecule that's polar. Now if a molecule is bent, as long as these are polar bonds, then this is going to be a polar molecule. It doesn't matter if these atoms are the same as each other or not. Even if they're the same as each other, their poles don't cancel and there is a net dipole moment. If they're different than each other, then it's still polar. Now, let's look at three bonds to the central atom. If you have a trigonal planar geometry and all the atoms are the same as each other, their poles cancel out and it's nonpolar. If it's trigonal planar and one of the atoms is different than the other two, then they're probably going to have different electronegativities. They're going to have different strengths with which they pull the electrons, and the poles won't cancel. This will be a polar molecule with a trigonal planar geometry. You could also have a trigonal pyramidal molecular geometry. There's a lone pair of electrons up here, right? And as long as these are polar bonds, whether or not the atoms are the same as each other or not, the molecule will be polar. Same thing goes for the T-shaped. There's two lone pairs up here. Even if the atoms are the same as each other, or if they're not, as long as these are polar bonds, this will be a polar molecule. For four bonds to the central atom, we have a lot more possibilities here. We have three tetrahedral possibilities. One, all the atoms are the same as each other, and even, we're assuming these are our polar bonds. The poles cancel in a tetrahedral geometry, and this is a non-polar molecule, even though the bonds themselves are polar. If one of these atoms is different than the others, we're assuming then that it's going to have a different electronegativity, and now this will be a polar molecule. Same thing if there's two atoms that are different than the other two, then the poles don't cancel, and this is a polar molecule. Now if we have seesaw molecular geometry, so there's a lone pair of electrons up here that we won't see. Again, as long as these are polar bonds, then this will be a polar molecule. The poles don't cancel. Square planar, there's two lone pairs on the central atom that we can't see. This is octahedral electron group geometry. And we have some possibilities here. Let's see. Let's start out with all the atoms being the same. These are all 90-degree angles, 180. all the poles cancel, it's non-polar. If one of the atoms is different than the others, assuming these are polar bonds, then this will be a polar molecule. The poles don't cancel. Now, if we have two atoms that are different than the other two, we have two possibilities. It depends upon where those atoms are. If they're like this, then the poles will not cancel, and this will be a polar molecule. But if they're opposite each other, like this, the poles do cancel, and now it's nonpolar. 5 bonds to the central atom. I'm only going to do some of these, and I'll leave you to figure out the rest, as well as 6 bonds to the central atom, because I think you're getting the idea now. Trigonal bipyramidal molecular geometry, all the atoms are the same. This is a non-polar molecule, even if these bonds are polar. One of these atoms being different, it doesn't matter which position that different atom's at. As long as we have at least one polar bond in here, that will be a polar molecule. 2 atoms, different than the other 3. Again, it doesn't matter. Well, it does matter here, really. If these two are on in the equatorial plane, if these are on these 3 in the middle, two of these here, then the poles will not cancel and it will be polar. But if they are what we call the axial positions, the ends here, the poles will cancel and this will be a non-polar molecule. Now what you should do is you should see what you can do with there being 6 bonds to the central atom and figure out the different permutations there.